All right, so let's continue with linear programming now, and I hope you'll enjoy the new feature in today's video. Uh, as you probably noticed, I haven't been posting too many videos for MME 350 this week because I've been focusing on my graduate class. I thought I would do a week's worth of lectures for them, and then start on 350 videos. And as you might expect, given my proclivity for distraction and so forth, I find it very disheartening to stand here in my home office talking to myself. So I've added a new feature for today's video. I hope you enjoy it. All right, so linear programming. Uh, we'll first talk about the formulation. It involves a number of additional elements that are not, or at least that we haven't covered yet in the nonlinear programming context. So you'll see where these come in. And again, I keep mentioning this, but normally in most other settings we would discuss linear first and then nonlinear. And we did that earlier when we were talking about systems of equations, for example. But the reason why we've done nonlinear first is because we could kind of push off some of these more complicated issues in optimization that don't necessarily arise in nonlinear programming, but do necessarily arise in linear programming. So there's a few reasons here why, in practice, linear programming problems are actually more difficult to solve than nonlinear programming. Now, as always, linear is easier in a fundamental sense, but because it's easier, that leads, for example, to my first comment is that because they are easier, linear programming problems that is, they're often much larger. So by larger, we mean more complicated optimization problems in general, possibly many more design variables than would be the case in a nonlinear setting. So that the problems are much bigger, in part because they're in some fundamental sense easier to solve. Secondly, because the linear equations do not have finite extremums, they actually require constraints. So in the context of nonlinear programming that we've been discussing thus far, we have kind of swept the constraint issue under the rug. We did talk in the last class and last video about Lagrange multiplication methods for constraints, in that case, equality constraints. But we have largely kind of left the constraint issue to the side. Now, for linear problems, which I'll make clear in a few minutes, they actually require constraints. There's no way to have an unconstrained linear problem. The other reason why this is the case is because there's just a lot of jargon. So when you get into linear programming, there's all kinds of issues that come up, and there's really a lot of jargon that we need to be aware of. So that's something you'll just have to get used to. Okay, so let's get started. So this, again, we're going to focus on the formulation. It involves a number of different components, and then we'll walk through each one in an example in this first lecture so we can kind of get a feel for how they all fit together. So we have a general algebraic optimization problem, and for it to be linear, obviously everything has to be linear. We'll discuss that. We start with an objective function, or sometimes, again, we've mentioned this before, sometimes people call it a cost function. So that's J or F. And J is a function of all of the design or control variables, of which we have N. Now you're going to see there's lots of indices here. So there's capital N is the number of control variables, and then you'll see M and S as we go through the general formulation. So once we have the objective function, we also have equality constraints. So we'll denote these by G. So F, G, and H. F is the cost function or objective function, and the G's are the equality constraints. There might be one, there might be some number of them. We'll say that there's capital M of them. So those are some algebraic relationships between some of the control variables, but the point is they're equality constraints. There's an equal sign in the constraints. We may also have inequality constraints, and we often do. So it's the same idea. We'll now call them H, and there are S, capital S of them. So little s will be our index going from 1 to capital S, just like M is our index going from 1 to capital M. So h is a function of all the control variables, but now they are inequalities rather than equality constraints. We will also have positivity constraints, and that just means that all of our design variables have to be positive. Now, obviously, not every problem that we can imagine in terms of optimization will have positive values. We'll talk about that. They're not always going to be less than or equal to. We'll talk about that. They're not always going to be minimization. We'll talk about that. So we'll talk about all the various possibilities and variations on this as we go through it. So these constraints provide restrictions on the values that the design variables can have. So for example, a rocket engine. So obviously you can't have negative thrust. So the minimum value of thrust is 0, so it has a positivity constraint. And then there's some maximum thrust that a particular engine can put out. So that's an inequality constraint. It has to be less than or equal to that maximum thrust. A company's profit can't be larger than its revenue. And unfortunately, it can be negative. Oh, bummer, my app wasn't ready. So you can't have a negative profit, and the profit can't be larger than the revenue. So that leads to constraints, inequality constraints on profit. If you're manufacturing things, you can't manufacture a negative number of widgets, for example, so that would again be a positivity constraint. Now, if all three of these functions, f, g, and h, if they're all linear, all of them have to be linear, and if they are, then it's a linear programming problem or a linear optimization problem. If any one of them is not, if any one of them is nonlinear, then it is a nonlinear programming or a nonlinear optimization problem. And we've seen some examples of this earlier in this chapter, but when you have nonlinear programmings, there is one special case, and that is when the objective function is a quadratic, so basically a parabola, so a second order polynomial. And so if the objective function is quadratic, but the constraints are linear, then we call that a quadratic programming problem. It's still fundamentally nonlinear because it's a quadratic, it's a second order, it's not a straight line, but nevertheless, it does have some special properties about it, some of which we've discussed before. So then our primary task here is then made to develop methods for incorporating these various types of constraints. And again, this is what makes the linear programming problem a little bit more difficult than programming. So we're going to take advantage of our linear algebra knowledge. We'll define the design variables as a vector x. So x is a vector and it consists of all capital N of the design variables. And then in the linear case, where f, g, and h are all linear, then we can express the objective function, j, as a linear function of the design variable. So you see just a constant times x1 plus a constant times x2, and so on. All of the terms in the objective function are just constants times a design variable. No squareds, no x1 times x2s, no signs of x1, nothing of the sort, because that would make it nonlinear. And so this can then be expressed in vector form as C transpose X, where C is the vector of the C coefficients, X is obviously the vector of the design variables, or we can, that's also, the C transpose X is also the inner product of C with X, or the dot product if you prefer, of C with X. So we can express it that way in linear algebra terms. The equality constraints, again, this is a series of equations. It might only be one, but there's in general m of them. They have an equality in them, so they can be written as ax equals b. So as a matrix A times a vector x equals a vector b. Similarly, the inequality constraints can be written as cx is less than or equal to d. Again, c is a matrix, x is a vector, and d is a vector. Then the positivity constraints, just like before, all the design variables are greater than or equal to 0. Now, based on the standard formulation that we had 2 slides back, where we have n design variables, m equality constraints, and s inequality constraints, then we can see what the size of each of these matrices and vectors are. So C, the vector C, is, again, it's a vector, and it is of size n. So it's of the same size as X. It has n elements. The matrix A is M by N, so Mary by Nancy. B is M, Mary by 1. And C, the matrix C, is an S by Nancy matrix. And D is an S by 1 vector. So if you go through all the sizes in terms of matrix multiplication rules, everything hangs together just fine with those matrix and vector sizes. Okay, so in the linear case then, if we have two design variables, then we essentially just have a straight line. And if we have more than two, so 3 or more design variables, then we have a planar surface. The point is that in either case, the objective function does not have a minimum in the normal sense. So if you take the derivative of a straight line, of course, you just get a constant. So the slope is a constant, and it's generally speaking not zero. If it is zero, then the whole thing is zero, not just at a point. So you have a straight line or a plane, and it's at some angle. And so the minimums and maximums of such a line or surface, planar surface, are at infinity. They're unbounded. So that's why we have to have constraints, either equality, inequality, and or positivity constraints. We must have constraints to limit the values of the variables. Otherwise, the minimums would be literally negative infinity and maximums would be positive infinity in all cases. So you have to have a constraint to keep it from going all the way to infinity. So here we go, some more jargon. So when you define the constraints, when you impose the constraints, the space, and we'll draw this graphically to see what this looks like in a small case. The space is called the feasible space or the feasible region. So this is the space in, say, x1, x2 space where the optimum could be based on the constraints. We'll go through an example and show what that means. So the feasible space in linear programming problems is hopefully a closed polygon or polyhedron. So it's a closed shape. There's no gaps where the minimum could run out all the way to infinity, negative infinity. And so it's closed and it's in the shape of a polygon. So it has straight sides, any number of straight sides. Then the feasible point, so we have the feasible space, and then within the feasible space, there's the feasible point that happens to be the minimum. So the feasible space is all of the possible minimums, all the possible points x1 through xn that could do satisfy, let me start over, that was a mess. So the feasible space is not considering the objective function at all, just looking at the constraints. Based on the constraints, it's the region in the design space where the minimum could be, where the optimal solution could be. So it's all the values, that's why it's a space, a region. It's all the values of the design variables that satisfy the constraints. Then, when you impose the minimization of the objective function, that will hopefully leave only one point in the feasible space which minimizes the objective function. So that's the feasible point. The important point to get from this is this will be at one of the vertices of the polygon. So if you take any polygonal shape, so just imagine an octagon or whatever your favorite polygon is, and you put that, so that's on a flat planar surface, and you rotate it to some angle, right? So at that angle, if you were to put a marble inside your polygonal space, it will fall down to the lowest point. And that point will be at a vertex. Now it's possible that it could be that such that a whole line between two vertices is at the same lowest level, but that's very unusual. So we're pretty much going to ignore that. So one vertex of the polygon or polyhedron will correspond to that feasible point. Again, we'll see how this works out in an example. So some more comments on the formulation itself. One of the important things is and this can be a bit confusing when you first start doing these problems, is how do you decide whether an algebraic equation should be your objective function or whether it should be your constraint, one of your constraints. And so just simply ask yourself the question about that particular algebraic equation. For each one, typically you'll have more than one. So for each algebraic equation, just ask yourself the following simple question. So is it true that the algebraic equation has to be satisfied? If it has to be satisfied identically, then it must be a constraint. So if you're saying that in the example we're going to look at in a minute, the number of train cars in two trains has to add up to a certain value, that is a constraint. In that case, that's an equality constraint. If it is such, instead, if the algebraic equation is not such that it has to be identically satisfied, but it defines, say, a cost, or it defines the profit, or it defines the objective, the thing that you want to optimize, then it should be the objective or cost function. The problem is, this is what I'm getting at, the problem is they both look the same. They're both just algebraic equations. The key is to understand what is their purpose in the context of the problem. So secondly, optimization problems are typically framed in terms of minimization. We've discussed this before. So we're minimizing the objective function. If it's instead, say, maximizing profit, then all you have to do is take your j, your objective function, and multiply it by -1, and that will switch it from being a maximization to a minimization problem. So it's very simple, very straightforward. It just literally just changed the sign. Third, if you have an inequality constraint, which is expressed as a greater than or equal to rather than or less than or equal to. So if you look back at our standard formulation, it was in terms of a less than or equal to. If naturally you have a greater than or equal to instead, then all you have to do is multiply by -1, because multiplying an inequality by -1 switches the inequality from, in this case, greater than or equal to less than or equal to. And then finally, we talked about the positivity constraints. If a design variable's value could be less than 0, or say its minimum is greater than 0, then all you have to do is just simply shift the value such that in the new variable it's 0. So say that the minimum thrust, you can't operate your rocket at a thrust of 0, it has to be on, and the minimum thrust is 100 kilonewtons, or whatever it happens to be. So then you just shift that variable, that design variable, so that instead of 100, it's shifted to be 0. Okay, so using all of these rules or changes to the problem, we can change it from being something other than a linear programming problem in standard form to being in the standard form. All right, so let's look at an example to see how this works. So let's say we have two train engines, 1 and 2, and they incur different costs per car. So we have a total of 100 cars that we want to transport from one location to another between the two trains. So, okay, well, we'll get to that in a second. And we want to minimize the total cost. So we want to figure out how to divvy up the 100 cars between the two trains such that we can minimize the total cost. Now, the first train then pulls X1 cars, while the second train pulls X2 cars. Okay, so let's go with what we have so far. Well, obviously, positivity constraints apply here. X1 and X2 both have to be greater than or equal to 0. You can't have less than 0 cars on a train. So X1 is greater than or equal to 0, X2 is greater than or equal to 0. In addition, the maximum number of cars that can be pulled is going to be defined such that on train 1, it can't be more than 50. On train 2, it can't be more than 75. So the first engine, train 1 engine, can only pull up to 50 cars. Train 2 can only pull up to 75 cars. And then finally, the total number of cars obviously has to be equal to 100. So that leaves us with an equality constraint, x1 plus x2 is 100. So we have our positivity constraints. You can see we're kind of working backwards here. We have our positivity constraints, x1 and x2 are positive. We have an inequality, actually two inequality constraints. We can't have x1 be more than 50, x2 be more than 75. And then we have an equality constraint that the sum of the two trains must equal to the total 100 cars. All right, so given these constraints, we'll come back and we'll talk about the objective function in a little bit, but let's just look at the constraints first and see how that defines our feasible space. All right, so let's draw the feasible space. So we have two design variables, x1 and x2. So x1 will be the horizontal axis, x2 will be the vertical axis. I'll try to do this somewhat to scale. So this will be 0 and 0, and then let's do, I want to get up to 100. So let's make this 100, and this halfway between will be 50, and then halfway between those will be 75 and 25. All right, so like I said, we'll try to kind of get this to scale. So then we have 25 and 50. So that's all we need. Okay, so let's just walk through each of these constraints. So 616, we have two positivity constraints. x1 is positive and x2 is positive. So based on that, if x1 is positive, that means it has to be to the right of the x2 axis. And between, actually let me use a different color here. So it has to be to the right of the x2 axis. Similarly, it has to be above the x1 axis. x2 has to be positive as well. Okay, so the feasible space has to be in the first quadrant of the x1, x2 plane. All right, so that comes from 616. Great, let's go back. Okay, then we have our inequality constraints. x1 is less than or equal to 50. Actually, let me be smart here and change these colors. Ooh, Castle, you're getting good at this. So these were the red, and then we'll pick a different color. Let's try yellow, see if that even shows up. No, not very well. Let's pick a color green. How are we doing there? That's a little better. So the green will be our inequality constraints, x1 less than or equal to 50, and x2 less than or equal to 75, and that comes from equation 617. All right, so our x1 has to be less than 50. So that means to the left of this green line. So that comes from, again, 617. Similarly, x2 has to be less than 75. So that gives us the upper limit there. So you can see how as we incorporate each additional constraint that's supplied by the problem, we're narrowing in, we're focusing in on the feasible space. Okay, so that was fun. Let's try the next one. We still have one more. Let's make this one blue. All right, so this says that x1 plus x2 has to be equal to 100. Well, that's a straight line, so let's figure out what that straight line is on our feasible space. So the x-axis, sorry, the y-intercept is 100, so that's right here. It's going to go through 50 at 50, so that's right here. So as we go down here, we see that we cross the boundaries of our feasible space at these 2 points. I'm going to call these A and B. Okay, so this is 618. So once again, you can see that as we apply each constraint, we zero in on a smaller and smaller feasible space. Now, in fact, because of the equality constraint, we actually have this line segment between A and B as our feasible space. It has to be somewhere along A, B, that line. All right. And you can pause there if you need to work through, make sure you understand all of that. All right, there we go. Okay, so let's talk this through and add in our cost function as well. So the cost function is saying that we want to minimize the total cost of the two trains pooling their respective numbers of cars. So now I said 10 and 15 in the original problem. I didn't get, that could be dollars, that could be millions of dollars and millions of dollars. It's actually more fun to think in terms of, let's just say it costs $10 million. So $10 million to pool each car. So on train 1, that's 10 times x1, and on train 2, that's 15 times x2. When you sum those together, you get the total cost of the two trains pooling their respective numbers of cars. All right, so that's fine. And now this is the constraint. Sorry, this is the objective function. So again, when you're working your way through these, just ask yourself, is it something that must be satisfied, such as this, or is it something that you're trying to make as small or as big as possible, such as this? So cost, we want to minimize the cost, so that's the cost function. Okay, so we have our j. It's a function of the two design variables x1 and x2, and we want to minimize that, but adhering to the constraints 616 through 618, which again, positivity, inequality, inequality constraints. Now, when you enforce then these additional constraints, it further confines the design space, and that's what forms the feasible space until, as we said, we end up with just this line segment between A and B being our feasible space. It has to be somewhere along that line. Now, in order to visualize the cost function on the feasible space, you could draw lines of constant j. So this is just a line in the x1, x2 space, just as this was a line in the x1, x2 space. So we could draw lines of constant j. And if we did that, this is not correct, but if we did that, those would just be parallel lines on the feasible space. And we want to find the line that gives us the smallest value of j, but while being consistent with and in the feasible space. So these are parallel straight lines overlaid on that feasibility plot. I won't actually do it because it just gets confusing. Now in our case, it's actually quite easy. So if you take everything that we've said together, the feasible space is, I said, was a line segment. In fact, it's actually either point A or point B, because remember, the actual optimal or feasible point is always at one of the vertices of your feasible space. So that means it actually has to be at A or B. It can't be anywhere in between. It has to be A or B. So in this case, this simple way to solve it is just evaluate for A and B, J, the total cost. So for point A, that corresponds to x1 being 25 and x2 being 75. So 75 and 25. Likewise, for B, that corresponds to x1 being 50 and x2 being 50 as well. So 50 and 50. When you put in 75 and 25 for x2 and x1, you get j as 1,375. So that would be if our currency is millions of dollars, then this is $1.3 billion to haul these train cars. Then for point B, where we have 50 and 50, you put those into the cost function, you get a cost of 1,250. So which one's smaller? Clearly this one is smaller. So point B corresponds to minimization of the cost function such that all of the constraints are satisfied and therefore that's the optimal solution. So the optimal solution is put half of the cars on the first train, half of the cars on the second train, and you're done. All right, now in practical optimization problems, the number of design variables, the number of constraints, whether inequality or quality, can be quite large. So here we've only had 2 design variables. They could be in the hundreds, they could be in the thousands, sometimes even in the millions. So generally speaking, it's not possible to visualize the feasible space graphically on a piece of paper as we just did. So we can do that for these simple cases with 2 design variables, and we'll do another example in a subsequent lecture. But generally speaking, we can't draw it graphically like this. But the same principles hold. So it's a plane in a multidimensional space on some angle, and you have to have the constraints, and the lowest point in the feasible space is the optimal solution. So because of this extra complexity, though, we're going to need a more algorithmic approach to working our way through this process, and that's called the simplex method, which we'll discuss in a later slide. Okay, so that's the basics. Next, in our next lecture, we'll talk about slack variables, which is how we treat inequality constraints. So we'll go over that in the next lecture.